Hi everyone, my name is Thibaut Cuvelier. I'm a PhD student at Centrale Supélec, a component of the Paris-Saclay University. I will present our paper, Statistically Efficient Polynomial Time Algorithms for Combinatorial Semi-Bandits. Combinatorial bandits are a part of the larger field of machine learning, which is about the question, how do computers learn from data? The major part of supervised learning is learning a static relation between a given input and an output. For example, you might want to predict the traffic on a given highway. For that, you will be using as your data previous traffic measurements for this highway or maybe other highways. Reinforcement learning is a completely different kind of learning when you want to train an agent to act in an environment. So for example, you want to train an agent to play a video game. In that case, your data will be a sequence of actions that you took in the game and the final score that you could achieve. So the really specificity of reinforcement learning is to take sequential decisions that are based on the experience that you had with your environment. Combinatorial bandits are a specific part of reinforcement learning where you have a strong structure for your decisions. So for example, if you want to choose a route from home to work, more specifically, I will present the combinatorial bandits with the example of navigator systems. So for example, Waze. How do such systems determine the best path for you to take from home to work? This problem is really easy once you know the congestion everywhere on the road network. However, that's really the catch. How do you know this congestion? You don't really have a lot of sensors to get this congestion. So what you have to do is to send drivers on the roads and to measure the time that they take to traverse a given road to estimate the congestion. There you have the exploration-exploitation dilemma. If you use a driver to explore a path about which you have almost no information, and that path is actually very poor, then this driver will be unsatisfied because that person is using your application to have a good commute time, and you're using a very poor path for this guy. On the other hand, if a driver can benefit from the exploration that all the other drivers did, then this driver will be really satisfied because they will have excellent commute time, but they won't really be useful for your ecosystem because they won't provide a lot of information for other users. This problem can be formulated as a combinatorial bandit. In that case, what you want to take is an action that is a path from the user's position to the destination. Before diving into the details, I will give some vocabulary that's really specific about bandit algorithms. So a bandit policy places actions in a combinatorial set. So for example, an action could be the way that you place ads on a web page. And the corresponding combinatorial set is the set of all such matchings. A bandit is used to play actions, and each action gives some reward. For example, for ad placement, you can get a reward of 1 if the user clicks on the ad and 0 otherwise. A very specific part of combinatorial bandits is that actions are decomposed so that they are made of several sub-arms. For example, such a sub-arm could be an association between an ad and a position on the web page. And you can learn very meaningful information about each sub-arm. For each bandit problem, there is also an optimum action, the one that gives the best reward. The difference in reward between any action that you play and the optimum one is called the gap. And the total difference in reward between all what you played and an optimum agent that only plays the optimum action is called the regret. This regret is the main performance metric for bandit algorithms. Because if you have a very low regret, that means that your bandit is playing optimal. But why is this problem interesting to study? First of all, there's the adjective combinatorial, which is related to combinatorial problems. And these problems are already quite hard. So the goal in combinatorial optimization is to find the best solution for known costs. For example, you might want to find the shortest path in a graph when the costs are the congestion on each road. In general, these problems are very hard, meaning that you don't have a polynomial time algorithm to solve them. You have many interesting exceptions, such as the shortest path or matchings. On the other hand, with Bandits, you're going into the uncertain world. And in this case, you've got to find the best solution for unknown costs. And just not unknown costs, but you have to learn these costs. And for this, a major tool is nonlinear combinatorial optimization. And in this case, you have very, very few exceptions where you can find a good solution in polynomial time. That means that up to now, there's been some general belief that you had to make some trade-off between time complexity of your Bandit policy and the performance measured at zero grades. And the result of this work is to show that you don't really need to make such a trade-off. So now let's dive into the details, the algorithmic details of combinatorial bandits. In general, for bandit algorithms, a good policy is to use the principle of optimism in the face of uncertainty. That means that you will always play the action that has the best combination of the average reward and confidence bonus. When you have an action that's barely played, you know that your average reward is probably not really well estimated. So that means that you need to have a high confidence bonus to have some incentive to play this action. Reversely, if you have a very good estimation for the reward of an action, you don't need a good confidence bonus. Otherwise, you would have to explore a lot of actions that you know that are not that good. When you apply this paradigm in combinatorial bandits, you can get to an algorithm such as ESCB, which is the following. At each round, you play a combinatorial solution that maximizes the sum of the average reward, here the term in blue, and of the confidence bonus, the green term. The computational problems come from the green term because this one is nonlinear, and that's really the source of all computational problems for ESCB. Our paper proposes an efficient implementation of ESCB that runs in polynomial time. And that's really the crux of our algorithm. We have a regret bound that's close to that of ESCB, but this one runs in polynomial time. The idea behind our algorithm is to approximate the optimization problem behind ESCB with budgeted optimization. So we move the complicating part of the objective function as a new constraint. Here, the constraint in green and blue. And this constraint becomes linear because of the structure of the objective function. We optimize this problem for a series of values of the budget. That means a series of trade-offs between the average reward and the confidence bonus, and we take the best solution. There are two problems with this formulation on the road to have a polynomial time complexity. First, we need to have a quite low number of values of budget to test. And second, we must be able to solve the budgeted problems quite efficiently. First, for the values of the budget, we decided to use scaling and rounding so that we introduce some approximation into the formulation, but we now have only integer values with some interesting upper bound on the value of the integers, so that you only have a very restricted amount of budget values to test. Second, to solve the budgeted problems, we write dedicated algorithms for each combinatorial problem. This technique works very well for quite a lot of interesting combinatorial problems, such as knapsack, shortest path, spanning trees, or matchings. Usually, these new algorithms are exact, meaning that it can yield the exact solution to the budgeted problem, but not always. And if we cannot get an exact algorithm, we devise approximation techniques that give an approximation factor. This approximation factor only has a constant impact on the regret of AESCB. So that means that we are still approximately with the same regret as AESCB using our technique. And now it's time to go to the practice of AESCB to see how good it performs in practice. We designed AESCB such that it should be able to run faster than ESCB and preferably much faster than ESCB in very large dimensions, but also so that AESCB has a regret that's really close to that of ESCB, probably slightly worse due to the approximation we had to introduce. We compare to a really state-of-the-art implementation of ESCB based on the state-of-the-art optimization solver Cplex, because it provides some nonlinear features that are sufficient to implement ESCB exactly. This solver usually runs very fast in practice, although it doesn't have good performance guarantees. We also compare AESCB to other algorithms, which are CUCB and Thompson sampling. These algorithms run much faster, but they have very poor performance guarantees. So the first part of the evaluation is the runtime. When you check in low dimension, both ESCB and AESCB run very fast, so there's nothing much to see. This is why in this table, I only focus in really high dimension. And you can see that AESCB always runs faster than ESCB with a much lower variance. So that's really interesting if you want to implement ESCB in a practical system. You know that the performance will not vary a lot as opposed to ESCB. The second part of the evaluation is the regret. Here I'm plotting the regret as a function of the time for the 4 algorithms. In blue, there's Thompson sampling. In orange, there is CUCB. ESCB is in yellow, and AESCB is in purple. What you can see is that Thompson sampling has a very high variance, even though in general the algorithm is very competitive. CUCB is by far the worst algorithm, and AESCB is extremely close to ESCB. So that means that ESCB works exactly as we designed it. But we can also take another view on our work, which is optimizing nonlinear functions on a very specific combinatorial problems. So actually, what we did is to optimize an objective function that has a really specific form. First, linear parts, then an invertible unary function applied on another linear function. We don't really need to suppose that this unary function is convex or concave for the same methodology to work on other kinds of problems. By itself, although, our approximation scheme does not always yield polynomial time algorithms. We need a lot of hypotheses to ensure that our decomposition techniques yields polynomial time approximation algorithm for any kind of nonlinear combinatorial problem. So getting more into the details, here I'm considering that f, the nonlinear function, is increasing, but you can do exactly the same for a decreasing function. We first find the range of values that f can take, and then discretize this range to some precision that you can tune epsilon. So now you have a range of integer values for f. And then you can optimize a series of budgeted problems, one for each of the values of f that we have computed. Finally, we take the best decision according to the original nonlinear objective function. This is a polynomial time algorithm only if the range of values for our nonlinear term is bounded by a polynomial interesting variables, and if we can optimize the budgeted problems in polynomial time. So as I hinted earlier, there are many interesting cases where this happens. For example, let's take the example of knapsacks. So a knapsack problem, you have to pick a given number of items for a total weight less than a fixed threshold. and you have to maximize the total value of the item that you choose. The standard algorithm for this problem is dynamic programming. So you define a simple MIW, where you consider items between 1 and I, and a maximum weight of W. And you have to take the decision about the item I. Either you don't take the item I, or you can add the value of this item to a previous value that you already computed. You can extend this exact algorithm to the case of a budgeted problem. In this case, what you have to consider is the third index for the minimum budget for your solution. You still have the decision to take the item I or not. And you have to change a bit the recursion to consider the budget of the item that you just took. So with this, and based on the bounds that you can define, you can still get a polynomial time complexity for budgeted knapsacks. So that's all what I wanted to present today. I hope that you could see that combinatorial bandits are a hard computational problem. It's not really easy to find an algorithm that works in polynomial time. AES-CB is a fast algorithm that achieves very low regret. It's not asymptotically optimal, but it's an algorithm that you can implement in practice to have good regret with really strong theoretical guarantees. We solve all the computational aspects of combinatorial bandits with a novel methodology to decompose nonlinear combinatorial problems into a series of budgeted optimization problems. Here are the references if you want to dive deeper into the details. And that's all for me. I don't know if you have questions, but now is the right time to ask them. Thank you.